I'm with BeagleBoard.org. We're now 10 years old with BeagleBoard. This is our 10th year in existence. We're a nonprofit foundation. I still have a day job. I've got the best job in the entire world because I get to be an entrepreneur without taking any risk. I get to do crazy, fun, passion project things, but I've still managed to keep a salaried day job, but part of that is I think that I've taken this. My focus is on access, right? Access meaning education, openness, enabling other people to do things. That's been very compatible with the company I work for because they can go and people make cool things, they sell cool products, but along the way we've seen just people do amazing things. In the last 10 years, there's Beagle Bones on the International Space Station. There's JPL prototypes, Mars rovers with them. I could talk about projects, and that's probably a lot more interesting than what I'll actually talk about. But I wanted to talk to you today about ways in which single board computers we're working with a partner now, Octavo Systems, to do system and packages to try to make Linux computers easy for you to make, as easy as like microcontroller systems. And I'm not going to spend a whole lot of time on saying why I think that's important, because I think it would take a while. But I think if you start just looking around at what's happening with the single board computer world and the exploding availability of different boards, and there's some motivation what you can do with a collaborative software base, as opposed to copy and paste of code, but actually just run the same code. Run the operating system, get the known software stacks that work and talk to the different devices, rather than trying to cut and paste and try to, hopefully connect things back together and hope they work again. But if you actually start from a working system, namely Linux, there's a ton of different boards out there with processors, every type of connectors. There's these, right now where we have a wonderful situation where you've got, just to name a few names like Grove and Microbus and PMod and like all these different things where then you have hundreds of different sensors that have all the exact same wiring that you can get to them real easily, and you have thousands of sensors supported in the Linux kernel, and you can find a board that kind of does the configuration that you want, or you can make it easily, and there's a lot of support out there from people in communities where you're not going to be the first one to kind of pave the way. With BeagleBoard, there's, I think, for BeagleBone Black projects, there's 35 different books out there, and everything from home automation to, if you want to build your own sprinkler system, or if you want to build robots or anything, there's a book out there to kind of get you started. So there's a lot of places to get started. There's kind of this explosion of the community and around the Linux computers, and when you're going and making a hardware design, we're in a real situation, and this is kind of flipped everything on its head a little bit, where software is really driving the hardware making decisions. Because I've got this quick prototype I can go together, when I actually want to go and make something into a product, the software guys are kind of dictating, I need the hardware to run this software, right, that's already there. And if there's not already a software solution, in the hardware, you just don't run that hardware, right? If you just you don't take the approach of, I'm going to write everything. You're going to look for things to be put together already. And so there's a lot of platforms out there that are providing great starting points, where you're going to focus on your value add rather than trying to rebuild the table stakes. And with that responsibility that a software developer now has in kind of dictating the platform, they need to start understanding more about the hardware platforms that they are dictating. And the big thing I'll point out is this need to look for open hardware, right? Don't choose a design where ultimately you don't have control of the supply chain. You can't actually reproduce the design. You're going to get stuck and essentially be out of control because you built on a set of software for which the hardware is out of your control. And so this has been our latest effort to try to go and do that. And it's the way we think it. There's a board is the solution for everything. That's just where our mindset is. But this is one of those, right? So this is a gigahertz Linux computer with microcontrollers and analog digital converters, CAN bus controllers, UARTs and SPIs and all the crazy I/O capabilities, in something that fits in the little mini Altoids tin, right? And so this is an entirely open source design, and it runs all the BeagleBoard software, and you can wire it up. The cool thing about it is just you've got this design as a starting point for you to go and build your own systems. I'm not going to spend any time on the eye chart of features, but if you have any questions about some of the individual features, you can ask. The cool thing to me about this is because we worked with these guys to put all the complicated stuff inside of a SIP, it's real easy for somebody to go and make their own system. All you need to do is essentially provide some power. This can be anywhere from like 3 volts to 6 volts or something in that range. You need to provide a clock source that didn't get integrated. Pull some pins, high or low, in order to set what the boot mode is, to say where it's going to get its data from, and provide some type of boot media, right? You could potentially connect it up over a network, boot it that way. You could boot it over USB, so you wouldn't actually need an SD card. You just load it into internal memory. But you need some type of way to get the code that you're going to be running, and that's it. Did I miss anything? Power, clock, boot mode, image, and then you can leverage the software that's already written and know that it's going to run there. So you're not depending on a lot of complexity outside of here. So the idea is that this is something that's easy to work with as a microcontroller. I don't know if this really makes its point, but it's supposed to say this is like really simple, but I think I think it actually doesn't quite go. But this is just mostly just like this is the signals that it's coming up. Here you see there's actually nothing connected. It's just naming signals. But you've got the header pins just directly wired. You've got you've got pull-ups for the micro SD card, and you're just connecting the USB. You put this is just a static ESD protection device on there, and you've got USB. Just showing connections, right? There's really not much interesting here except for the reset button right over there, and this is just a feedback for the reset, and yeah, that's the boot mode selection register. So it's a really simple circuit, and that's a whole Linux computer, right? So that's running a high-level operating system and everything, right? So you can run Debian or Ubuntu or all that crazy stuff. You could do all the layout in a single layer PCB, right? So or two layers, right? You need a ground plane. So you bring in the power. This is connecting the different power balls up to each other. You just need the power in, otherwise it powers all itself. So nothing. So really it's two planes, right? So this routing layer and then a ground plane underneath that. In reality, we didn't use this this layout for the PocketBeagle. It's something that we actually went with a 4-layer board in order to route the other traces on the board to get to all the different header pins. But I still think it can be. I still think it can be done in 2 layers. We just didn't push it that hard. You know, a 4-layer PCB is cheap enough. It really doesn't make any difference from once you make enough of them. 2 and 4 layers doesn't make that much difference. But it's standard, you know, really commodity in terms of. So a lot of you have done PCBs, you know, like this idea of 6 mil traces and 6 mil spaces. There's nothing fancy about that, right? And you can get that fabricated anywhere. You can probably even do it on personal mills. If you own a laser. Yeah. So, and the bring up process for this is really easy. We've got a USB-based bootloader. You could actually just with the USB connection, just load Linux, load like build root entirely over the USB connection using the onboard ROM. And this has changed, like, for me, like one of the scariest things of bringing up new boards was like that first time you boot up Linux was like, you know, because that was really nerve-wracking. You know, are the power rails right? You know, is the DDR right? Because the DDR stuff is complicated. And first thing I do is I boot Linux. I mean, just right away when bringing up a new board, and then I start messing with the I/O. I just use the sysfs entries, you know, to start probing GPIOs. And once you start learning the Linux tools, you know, this is working. Now you're just worried about the logic around it, right? What the peripherals are that you're connecting up to, and debugging those. And you're not like, there's no JTAG on here. I've never actually connected. If you've done board bring up, I've never brought up JTAG on a PocketBeagle ever. Right? We started by running Linux. That was our first debug. Did have to connect up the serial port. Working on trying to get where you don't even have to ever do that. But we did initially do that. You know, we've been working on trying to get the USB to work as essentially the UART for doing even the initial bring up. So real easy, and you know, you don't have to worry about bad voltages or DDR wiring or anything like that. If you screwed something up, it's going to be outside, and Linux will already run. I will say I did screw up one board design. I connected the wrong crystal. I swapped the 24 megahertz and the 32 kilohertz crystals once. That did make it not work. So you do need to provide the clock input. And then you got the complicated software-y stuff, right? This is probably the hardest thing for people doing work with the Linux single board computers right now is the fact that you've got all these embedded interfaces. So I2C, SPI, UART, and they're not self-discoverable like USB. Like if you're used to a computer, when you add a device to it, you plug the USB device in, the driver should just come up and it should just work. When you're working with embedded peripherals and sensors, it doesn't really work that way because the buses aren't self-describing. So you have to write this textual configuration to describe what's connected up on the bus, and that's what device tree is. And so this becomes kind of the hardest part because for the most part, the types of things that you're going to connect up are going to have Linux drivers already, even though everybody in the world has kind of written user space interfaces to all this stuff. Most of this stuff is already available in the kernel, and you don't have to go using any of that user space SPI or I2C stuff. Just find the kernel driver and instantiate it with the device tree entries. So this is what we find really being the hardest part. We've been working on ways to try to make this easier for folks as well. But if you go to this repo, we just kind of rebuild that on the target and reboot and run. And it works pretty nicely. I should be getting close to my time if I've timed this right. we've kind of put out a ton of different example starting points for people to work from, either using the BeagleBones themselves or taking them and doing other interesting designs with them. We've found that like one of the areas we're really used a lot in is robotics. So we actually did the BeagleBone Blue. This was we used lessons learned from the folks out of University of California, San Diego. They've been running robotics classes over and over again for years with a cape that they added on. So because we've got the integration, we were just able to put everything all into one board. So we've got a mobile robotics controller board. We've had other people do some custom things. 3D printing and machine control seems to be really popular. So the guy that did the Replicape is in the Beagle community. He's now done an all-in-one board called the Revolve, which I think you'll start seeing show up a lot in 3D printers, but also things like laser cutters and mills. There was one of the Hackaday Prize entries, Beagle Logic. So this is actually everything, like even the PocketBeagle could be a logic analyzer. Because you've got the microcontrollers on there that can do the sampling real fast. You've got the ability to send, to capture the large buffers of data. There's open source software. Drew, what's the name of what's the software? SIGROC, that's the one, thank you. Sorry, so yeah, you can use SIGROC to do actually all the protocol analysis and do the visualization. The guy that BeagleLogic also did a web-based interface, so you can get to the data over the web-based interface. But essentially, this is a $25 logic analyzer, or if you use the BeagleBone Black, it's a $50 logic analyzer, 14 channel, 100 megasample per second. But he did an all-in-one board that had some buffering on the I/Os. I brought a couple more outputs, so it's 16 channel. That one's called the BeagleLogic. But so there's a lot of derivative stuff. There's a lot of starting points that have come out this ecosystem. This is just the ones that are our boards. There's a huge amount of other stuff that's built based around the BeagleBone ecosystem that aren't specifically coming from us, targeting other types of applications. But this thing is where I really want to kind of highlight and emphasize to you guys, right? So. All the new stuff, we're making sure that we certify it as open hardware with the Open Source Hardware Association. And so these are our IDs. And that's really important when you're trying to pick things that you're building your designs off of, because without that, you're not able to really take control of your own destiny moving forward. I wanted to, have I timed it right? Do I have a couple minutes for questions?
Yeah, you're right on the money.
All right.
So,
3 questions. Does anybody have questions for me? All right. Thanks, Roger.
Maker, creating, building something, when do you... Okay.
So as someone who wants to get into this space and want to build something, what's your guidance on do a cape versus spin your own board?
Yeah, most of the time, you should start by doing a cape. If it's the first time you've kind of done something, I would start by building the cape. With something as the SIP, it's pretty easy to go and build your own board, but you could probably just do like point-to-point wiring or breadboarding type of solutions, depending on how complex your design is. You can get to a point where design is complex enough, you should go straight to your own board. What's the example of the threshold? Essentially, if you can't figure out how to breadboard it, I haven't run into that case personally, that you can't figure out how to breadboard something. Like we made the PocketBeagle headers so that you can actually take the microbus clicks and plug them in. You can plug 2 of them in on top of this directly without having to add any other rerouting of wires. And so that's like 450 different little add-on boards that you could use with the PocketBeagle without having to do any sort of relayout or even another another breakout board. So it's pretty small, so you can probably make it fit into most situations without needing to make something smaller. If you do need to make something smaller, just working directly with the SIP is the way to go. I can't think of anything actually where you couldn't start with the cape first. There's sometimes where you need to get some signals. Actually, that's probably more likely the case. For the PocketBeagle, I specifically didn't bring out the Ethernet or the onboard flash signals. So there's another MMC bus and some of the LCD control signals. Part is because a lot of times systems are going to want to use those if they want to, like if they're going to want to use those for those purposes. And so I didn't want to use those pins up. So if you built out on hardware, you'd want to try to depend on other signals than those, because the onboard flash is a really useful feature that a lot of people like in the BeagleBones, because it's a lot more reliable than trying to run off the micro SD cards. I don't know if I answered your question well enough. Okay, one or two more? Speaking of somebody who's built incredible things off of PocketBeagle, right? This you got to see what this guy has done with PocketBeagles. It's amazing.
So all these device layover stuff is always too complicated for me. Ideally, I would just like read the datasheet and just program it directly. But then the kernel gets into the way because it just claims things and whatever. So why this whole device overlay stuff? Can't we just have it simple?
Yeah, that's a Linus Torvalds question ultimately, because he's the guy that decided that we needed to have device trees. We've gotten rid of the dynamic overlays. It's still actually they're still there, but we don't encourage people to use them or rely on them anymore. So we do still apply overlays, but we apply them in the bootloader. So there's no conflicts. All the conflicts are essentially resolved before the Linux kernel is brought up. And that means if there's any resources that are utilized in the base device tree that you want to get a hold of, in the overlay, you simply disable those. And so there's no runtime conflict in getting to the hardware anymore. You simply, in your overlay, you specify those to be disabled, and then you apply yours. So there's no runtime, because you haven't booted the kernel at this point. There's no conflict, and you will get control in your overlay. The other thing we did on the PocketBeagle to try to make some of this simpler is that we booted up by default into a large number of pin modes. So we assigned pins to be UART and I2C and SPI and PRU. So the microcontrollers that are on here that add a lot of the capability that is BeagleBone, right, is this idea to do this real-time control stuff in the same time as Linux, that Hinner makes incredible use of in his PCB, LD Graphy. If you haven't seen LD Graphy, you should check that out. Those pins are already assigned functions, so you don't even need a device tree entry to use those as they're predefined. Unless you want to do things like load a specific driver or something that's not user space. Sorry if it's a little bit of a learning curve, but it's worth it, I promise. Last one from the back.
Thanks. What would be your best strategy to connect this board to the internet over 4G or some kind of cellular network?
Wow, that was almost a plug. The folks over at Hologram have already designed a cape for the PocketBeagle to let you do 3G networking using the U-Blocks modem and their SIM cards. So that's probably the easiest way to get into a 3G network, is to just use the Chris Gamble cape. There's also ways you can do it over USB directly. If you really don't want to have to wire anything up, they have splitters. This USB port is an on-the-go port. There's splitters that allow you to put power in but get the host function out, just using a standard cable. So that's an easy way. But you also have the UARTs on here if you want to connect up other modems over the UARTs. That is a really common use case, and I would plug the guys at Hologram for that one.
Awesome. Let's get a round of applause for Jason. Awesome stuff. Thank you so much.